Hey, wow, you guys are quick. Good morning. Let me get a pen. So I've got Kai and Alessandra and Julius and Kiara and Amelie. And I got Stella. And today is the 12th. So let's put a spot there. 12, 3. So we did nuclear accidents. Good. And I've also got Hannah. Good morning, Hannah, Ayala, and Inessa. Good morning, Corsine, Michael, and Aslan. Very good. And continuing. Good morning, X2 Dude. Better tell me who you are. Good morning, Charlotte. Michael, I gotcha. Hello. And Isaac, good morning. There's Aaron and Isaiah and Malta. And today's the 12th. Super. All right. Good morning also, Sophie and Linus and Sina. Nice to have everybody there. Let me focus you on the screen. Let's do a problem to warm up. Okay, you ready? Let's see if you remember this last time. So we've got, let's take U to 38, and we'll say it's 92 plus whoop, and then forms, let's say 3 neutrons plus plus RB. This is 37 at 85 plus energy. Okay, so while I'm taking roll, you guys want to warm up and see if you can fill in the blanks. See if you remember how to do this from last time. We've got uranium 238.92 plus a neutron makes 3 neutrons plus rubidium 37.85 plus something or other. Can you fill in the something or other right there? See how many of you can figure that out. Go ahead and do the math while I take roll. And where did I end up? I ended up with Sina. I got Sina then. And I got Clara and Jack. Okay, good. I got Jack and Cassidy. Good. Then after Cassidy, I got Liam, Ethan, and Felix. Very good. Put my periodic table here. And I got Paul, Zach, and Kiara, as well as Alicia. Good morning, Alicia. And Ingrid. Good. Glad to have you all here. That is quite wonderful. Happy Friday, everybody. Indeed, indeed. Okay. And while we're warming up, well, let's see. I'll let you continue. Go ahead. I got already one person working on the subtraction. So can somebody work on the bottom number? How many protons would this thing have? And the top number, how many neutrons plus protons would be the top number? Then figure out who it is. So continue, folks. There, Kai's working at it, and Liam's got to start there. So the answer is okay. So we need 3 things. We need the identity of the atom, its symbol, we need its bottom number, its atomic number, and its mass number at the top. Good. Okay, so, and Isabella's here too. Thank you, Isabella. And Alessia is here. That's okay. That's fine. You're still pretty much on time. Okay, so let's have a look. So the bottom number, anybody else want to put in a guess? I like lots of people to do it. The top number, they're saying 154. So let's check that one first. Okay, so, and Paul's got a different 151, 150, 53. All right, let's have a look, Paul. Okay, so I got 238 plus 1 be 239. 239, I got a minus 3. So that'd be what, 236? And then I got 236 minus 85. Oh, 236. I'm too sleepy. Minus 85. It'd be a 1. It would be a 1 here. 13 minus 8 is 1. 151. Paul, I think you got it. As does Inessa. So I think it's 151 is the top number. Okay, bottom number. Let's see. What did people say? Bottom number. Start as 92. Okay, thank you, Amelie. Tell Avram to keep trying. I hope he gets in. Bottom number. Alexander says 55. Let's find out. Inessa says 53, as does Kai. Okay, let's check it out. Avram made it. Thank you. Good, Avram. I'll mark you in a second. Okay, 53. So here we go. Isaiah has it too. 92 minus 37. Well, 12 minus 75. And it sounds like then, indeed, 50. I got 55 and 53. No, I got 53. Am I missing something? 92 minus 37. Isn't that going to end in 5? Or am I missing something, folks? 8 minus 5 would be 5. I think it'd be 55, wouldn't it? Oh, I know what I'm missing. I made a mistake. Somebody find my mistake. Anton is here as well. Let me mark a couple of you. Okay, that's fine, Lesia. All right, so my people, where's my mistake? This is right. It should be 55. Where did I goof up? I wrote something wrong. Aaron found it. Good job, Aaron. See that? A neutron has how many protons in it? Did I write the correct number? No, it does not have 1. What number should be down here for neutrons? Let's see if somebody else is following. What's Aaron talking about? What number should be down here for neutrons? Here too. Thank you, Alessandra, Chiara, and Aaron knows 0. So that is your teacher's mistake. So it really should be 55. Somebody look up 55. Who is that sucker? Who is 55, folks? So who is the identity here? It's element 55 and several have it. Good. Wow, you guys are so quick. Who was it? Alessandri, Nessa, Chiara, Ayala, Ethan, Kai. So many of you, I can't keep it straight. Ingrid. So it is cesium, CS. Okay, good. Then this is an example. Thanks everybody for participating. You're nice and awake. I like it. This is an example for what sort of reaction? It's a reaction. It's an example of a reaction. Ah, Corey's here, and as well Avram. Good. So, what kind of reaction was this? It's an example of a reaction. Let me write a couple people down. Corey, gotcha. Still missing Allie, and still missing Devante. And Tim Hartling, are you out there? Devante, are you out there? Allie, are you out there? Fission, thank you, Aslan. So it is a fission reaction. Remember, fission is breaking stuff up to make energy, right? Energy, good. So I gotta just write a name or two, and then I'm with you for the rest of our hour. We'll talk about our plan for this hour. Okay, so I'm missing. And Michael, are you out there? Michael? If you are, say hi. I don't know if I saw Michael or not. Okay, so this is 9F, so I need Michael, Tim, H, and then 9. Ah, Michael's there. Hi, Michael. Sorry I missed you. Thank you. Thanks for checking in. Still looking for Allie and Tim H. And in 9E, Matthias, are you out there today? Looking for Matthias and Devante. Matthias is there. Thank you, Matthias. Sorry if I missed you. Sometimes your names come so quick, I can't keep up. Got Matthias there today. Good. Okay, looking just for Devante. Okay, most of you are there. Let's go ahead and start. So, up till now, we've talked about fission. Fission. I want to talk about the other word and see if one of you knows what it is, okay? Let me lower that so you can see the whole board. I'm not so important, but the board is. Okay. It sounds really similar, but it's totally different. And it's this word, fusion. Fusion. Who knows what that is? What is fusion? Not confusion, but fusion. Leo is here too. Thank you, Leo, for checking in. Good. I'll mark you in a sec. See if somebody knows what is fusion. Hint, it's sure not fission. Well, I'll start you off. When two atoms, no, let's make it two nuclei are let's see if somebody's looked it up or if they know it. Zach, they combine, yes. And the merging, yes, Kai, they're merging together, so to speak. Yeah, combining elements. That's right, Alessia. Combining them together. Thank you, Kiara. Good. A lot of you have that. So many, I can't keep up. Okay, so when two nuclei are joined together, lots of energy is released. What do I mean by lots? You ready? Put a little star by lots. By lots, I mean it's about 10 times more energy. So I'll put 10x per gram of fuel than fission. We talked about last time fission power plants, and of course the problems that can happen at power plants. Oh, I don't know if we did this or not. I better ask you. I do have somebody here. Tim H is here. Thank you for checking in, Tim. Let me mark you down. Okay. Whoops, wrong page. There's my Tim. Good. Anybody else I didn't see? Okay, so question about fission. I meant to ask you this last time, but I'm going to ask you now. What's the main advantage for society for fission? There can be nuclear accidents and stuff, but normally there's not, to be really honest. Most plants run for decades without a problem. There's also nuclear waste, that's a problem. But what's the really good thing about nuclear power? What does it not make? What's the main advantage of nuclear power? So before we talk more about fusion, I got to ask you this about fission. The main advantage of fission is it doesn't make what? Let's see if some of you know. You get much energy without much material. Yes, Kiara, that's true, but there's another big advantage. Aslan, fossil fuels. What about fossil fuels? Give me a sentence, Aslan. Leo has it. It doesn't create CO2. So by burning fossil fuels like coal to make electricity, which is what most of the world does, we make a lot of CO2. Once the plant is working, we don't really make any CO2 out of it. Remember the products we made from our fission reaction today? I get neutrons, I get two other elements, but I don't get CO2 out of it. So no CO2 is a really big advantage for our world because that means we heat it up less. We have less global warming. However, if we can ever figure out fission, it also does not make CO2. So it has the same advantage. And it makes 10 times as much energy per gram. That's a lot. 10 times as much per gram. Woo-hoo! Sounds like a great deal, right? I'm going to give you a fission reaction. Okay, sorry, fusion reaction. Okay, I'm going to write that here so we know we're not doing fission. Fusion reaction. Okay. All right, I can take a hydrogen. Remember how small hydrogen is? Really small. It's only got 1 watt. 1 watt. One proton, right? One down here. So it's got 1 proton. Let's take a hydrogen that's a little unusual. Once in a while, you get a hydrogen that has a neutron. So not very often, but let's say it's got a neutron and a proton. So then I get a 2 up here. And I'm going to take another one. It's just got 1 proton. And once in a while, you have one that has 2 neutrons. So I get a 3 up here. And they can find this. Believe me, there's a lot of hydrogen out in the oceans, all that water. So it's not hard to find these suckers. Okay, it can be done. And what they make, well, let's look at what fusion was. 2 nuclei joined together. So I get what? What would be 1 and 1? What element am I going to make? Can you guess? Let me pause here and have you write it. A helium plus oops, sorry. I just said it. Oh, I hate it when I do that. A hydrogen plus a hydrogen makes, thank you, Alessandra, a helium. Thanks, Inessa, Charlotte. So it does indeed make helium. So look at that. Why? Because 1 and 1 is 2, right? You know that. And then the top thing could be a 5. It could also be a 4. And then I maybe shoot off a neutron or something. But that really doesn't matter. This time, let me put the right numbers there. Plus a lot of energy. Yeah, I'm going to write it really big. Energy. Make it nice and big. Try and make it less sloppy than me. Okay. So a lot of energy. Sounds like a great deal, right? Doesn't that sound like that's like the answer to human beings' problems on the earth? It is really a great deal. You guessed it, there's only one problem, and that's what I want to talk to you about now. Okay. What's the problem? What's the difficulty with this process? See if you can guess the difficulty while I'm erasing the board. It looks great. It would be wonderful, but what? All right, let's see if we got any guesses. I'm going to read your guesses here, okay? The nitrogen at the other side. No, that's okay, Charlotte. It doesn't really do anything. To be honest, in this case, it doesn't like cause any problems. It just goes off on its own. It's okay. Kiara, maybe you need certain circumstances to make it fuse. Yes, you're red hot, so to speak. Alessia, it's hard to find H's with those specific numbers. Yes, but they can do it, Alessia. There's so much water in the world, they can find those hydrogens. Too many neutrons? No, that's not a problem, Paul. I wrote fission, not fusion. Thank you, Kai. Everybody change your notes. Sorry. Thank you. Good catch, Kai. So, but fusion has a problem. Okay, so what's the problem with fusion? Sorry about the confusion. I didn't mean to do that. All right, let's start again. Spare neutrons. Nah, they don't really do anything, Paul. It's okay when they go out there. They don't really do much. That's not really much of a problem. Okay. Yeah, Oslo noticed that too. Thanks, you guys, for catching my mistake. Should be a 5 on top. No, it shouldn't, because I got a 4 and then I got a 1 over here. So for this 5 and 5. Okay, I got a neutron over here. So it adds up okay. All right, let's see if I got any other guesses. Fusing is harder because one wrong move on a fission reaction could happen. No, fission's not going to happen very easy. I only got hydrogen. I can't split that. It's already as small as it can get. Is it harder to control? Not really, that I know. An implosion, Yain, that would be a yes, but he got another thing. Resources? I don't understand, Clara, what you mean. Okay, let's draw it to give you guys a little clue, okay? Here's your hydrogen. Okay, it's got a proton and a neutron, all right? The neutron doesn't really matter, plus another one. So I'll do these guys. Remember, we're only trying to get these two nuclei together. What's the problem? Here, maybe I can do it this way. These guys, I want to shove them together. Why don't they want to get together? What's the problem? Waste, not really the problem, Paul. The fusion is permanent. Yes, it is, Michael, but that's not a problem. Look at this. Why don't these want to get together? What's the problem? These are two nuclei. This is my hydrogen and another hydrogen, right? Somebody usually comes up with it. Because they're not equal? No, that doesn't matter. That doesn't matter. Aslan, they repel. Okay, there's no electrons in my picture, so the nucleus is only what, gang? Positive. Remember the neutron doesn't do anything in there to the charge. You ever take two magnets, let's pretend these are magnets, and try and put the same poles together? They don't want to get together. Well, you know what? If I try and put nuclei together, they do not want to be together. These guys, and I think someone said the word, let's see if I see it. Isaac said the word, and maybe some others as well. And Leo said it, they repel. They don't want to get together. They're like magnets that you got to shove together, except it's a whole lot harder because you're going to make them together permanently. You're going to fuse them together. That's really tough. So how does it happen? Okay, let me read a couple more comments before we go on. Yes, exactly, Leo. Right. Yes, Isaiah, they repel. Does this repelling make the energy? No. The repelling is something, Kiara, we've got to overcome to make them get together. Once they get together, they release the energy, but they don't want to get together. Okay. to make them get together, they got to be moving really, really fast. So when they hit together, they fuse. How can I make them go really, really fast? What can I do? What sort of conditions do I have to make them go really fast enough to hit and join together? It's hard. How can I make them go so fast so they'll actually, whoops, hit and join together? That was more of a fission. Let's make it a fusion. So how can I make them join? Spin them around, kind of. I gotta. Okay. Clara has it. Clara says heat. Yes, Clara. I've got to heat them up. So these guys must be. So I'll say the nuclei. Well, the whole element, but the nuclei must be heated a lot, to put it mildly, to smash them together. Although, let me give you the science word for smash together. It's called collide. Bad teacher. Let's use the science word. So they've got to collide with a lot of energy. Where did I go? Nuclei must be heated a lot to smash them together, collide hard enough to fuse. Okay. High temperature. Exactly, Cassidy and others. Thank you. Thank you for jumping in there, Ingrid, Sina. So we got to heat them up. You ready? Here's the sort of temperature you need. You guys ever hear about the Kelvin scale? There's like Fahrenheit, which they use in the US. There's Celsius, which we use here in Europe and most of the world. And then there's a scale called the Kelvin scale. The Kelvin scale is kind of the same as Fahrenheit. It's just shifted about 273 degrees. Absolute zero. Okay, so Alessia and maybe a couple of you have heard about this scale. All right. It doesn't actually matter. I don't even have to use it, but I know that the number. Okay, what temperature we need? So I'll write temp required. You ready? 100 million degrees Kelvin. But we might could say Celsius too. It doesn't really matter. They're only 200 something apart. Or if you're familiar with the Kelvin scale, I'll write Kelvin. Okay, ladies and gentlemen, I need 100 million degrees Celsius. That's really hot. That's really, really hot. Okay? Do you see why it's so hard to do? Bummer, huh? Let's see what other comments you have. AP Prep, you had Kelvin. Okay, good, Michael. So then you guys know about the Kelvin scale. Yeah, massive amount of energy to make that temperature, Ethan. Yeah, exactly. It's not a question of evaporating. It's already a gas, so you're okay with the heat. They just got to be going, Ethan, really, really fast. Okay. So far on Earth, the only way they can do this is in the lab. So right here in labs, we can do this for small amounts of hydrogen. So with small amounts of H using lasers. Sounds like something out of a science fiction movie, right? Can you imagine a bunch of lasers focused on one point? Like there's my hydrogen, right? And we're going to focus a bunch of lasers all on this hydrogen to make it heat up enough to fuse. They've done this in the lab using lasers. You might say, oh, problem solved. Here's the difficulty, okay? It's another but. I'm going to leave the word but because now we got a new problem. Yes, they can do this in the lab, but let's see if some of you guess what the further problem is. It's difficult for one, but there's another problem. Let's see what Paul says. Uses a lot of energy to heat them. Yeah, the lasers use a lot of energy to heat up the hydrogen, but to even get more energy from the reactions, or does it take more? Paul. Beautiful. Paul's got the problem. The problem is energy. Okay. If I put in, I'm going to use numbers to give you an idea of Paul's idea. Let's say I put in 150 kilojoules to make this happen. And when they fuse together, they give off 100 kilojoules. What's the problem? So what is Paul trying to say here? I fuse them with lasers. It takes 150 kilojoules. They fuse and then they make 100 kilojoules. What's the problem? There you go. Thank you, Leslie. Lasers require energy, and the whole process, Paul, exactly loses energy. So I'll say right now, no one has gotten out more energy than they put in. Bummer. That would be a real bummer. Okay? Why? Because if we can do this, it is really a great, great, great thing. Let's see what others you guys. Yeah, so in a sense, it wastes energy, Tim, right? Because we end up putting in more than we get out. And of course, I can't run a city if I use more energy than I get out of it. What's the point in that, right? We want to create electricity, not just use it up. So it's kind of the opposite of a good power plant, isn't it? Let's see what else you guys say. The lasers need more energy than they produce. Exactly, Ingrid. Now you got it. That is it. Is there another method of fusing together without using so much energy? Kiara, exactly the right question. Okay, ready? So scientists are trying to figure out a way to do this at a lower temperature. And I mean, this is going on in these studies at many places around the world, okay? It's a big deal. And you can imagine it's a big deal. If somebody solves this problem, it's going to be a big, big deal, okay? It will change your life and my life forever. So scientists are trying to create fusion at a lower temperature, so they don't have to heat it up to like 100 million, okay? And therefore, to release more energy than they put in. I know this is a lot of writing, but you'll see why in a second. So bear with me. I appreciate you taking good notes on this. Let me read this off again. So scientists in red here, it's a little harder to read probably. Scientists are trying to create fusion at a lower temperature and therefore to release more energy than they put in. And let's see if somebody can guess what that's called. You might have heard this in the news. Called cold fusion. If I can spell fusion, right? This is a big deal around the world. You may, if you read newspapers or online sites, occasionally you'll see something about cold fusion. Many different scientists in many different countries are trying to achieve it. The first team that achieves it will be giving a huge gift to humanity. I'm not kidding about that. I'm really serious. Can you imagine the advantages of this? We're going to go through the advantages of fusion in just a minute, but this is going to be a big deal. How can you heat something and not make it that hot? Yeah, it's a good question, Clara. Or is there a way they can make the process happen, Clara, without heating it up to that temperature? Cold fusion, exactly. So if you've heard of that, that's what the world is trying to achieve. There's even a nuclear power plant that is being built now in Europe that should be using fusion, but it's not done yet. And even once it's done, no one is sure it's going to work. So it's a huge multi-billion euro power plant. And I'm not sure if it's a good idea or a waste of money. I'll be really honest, because I feel like they should figure this out in the lab first. A few years ago, there was a team in Utah at the University, Brigham Young University, that thought they achieved cold fusion. It was in all the papers, and then they found out their measurements were wrong. They hadn't done it. They still had put more energy in than they got out. So getting cold fusion is not easy. But if you can do it someday, any of you will be a hero, big time. Let's see if some of your other comments I can answer. Yeah, exactly. Let's go to some advantages, okay? Well, it sounds like you guys are ready to do that. If you got another question, type it in again. You have so much good comments. I sometimes miss some of your comments, okay? It's not on purpose. Good. So if we could have fusion, so if, the big if, we could have, I get so excited. How's our time? Oh, we're still doing okay. If we could have fusion, underline if we could have fusion power plants, advantages there's several. So what are some advantages for the human society if we could have fusion as our power source? What are some advantages? There are many. I'm going to look back. I think Kiara had one, but I don't. Yeah, okay, no disasters. Yeah. Probably. I don't know, Kiara, but I will say probably less potential for disasters. Because if you stop fusion, it just stops. It's not like it's going to go on its own, okay? Less potential for disasters. But there's a lot of other benefits too. What are some other benefits? Can you guess? Let me read now. You got it. Good. There's a bunch of good ones. Let me hurry up because you guys keep going. Then I missed somebody's comments. Inessa says no nuclear waste. You got it, Inessa, because the fuel's not radioactive. No, nuclear waste. So people are going to not say NIMBY. Remember, not in my neighborhood. So no nuclear waste. That's a biggie. And another biggie from Ethan. Ethan, less CO2. So in fact, if you look at the products, Ian, there's no CO2 given off. No CO2. I mean, when you build a plant, it would give off some to make the plant, but really, I'm going to say no CO2 emissions. Like nuclear power, it doesn't give off CO2 like burning coal does. Remember last semester when we burned hydrocarbons, burned alkanes and stuff, it always gave off CO2. This does not. There's none of that. So that would be a big help for the global warming, wouldn't it? As well as no nuclear waste. Any other things you can see that are advantages? Okay, Ingrid had that with CO2. It's easier to control. Because they can't do it yet, I'm guessing your answer, Clara, is yes, but I don't know because they can't do it yet. Ingrid says, no thermal pollution. Right-o. No hot water. No thermal pollution. I'll put hot water. Remember we said that all power plants give that off into streams and lakes, which is not so cool for the fish. Well, fusion would not do that, so she's right. What else? No lasting nuclear waste. Good, Leo. Yeah, we had that one. Not as dangerous and unpredictable. Probably true. More power, easier. Yes, that is the big point, right, Aaron? Okay, enough fuel, because the fuel is, remember the fuel for fission? It's uranium. It's not easy to find. What about the fuel for fusion? Kiara kind of said it. Fuel is easy to get and abundant. And abundant. That's a real biggie. The fuel is hydrogen. And we can get it from where? What do we have a lot of on planet Earth? Where can we get that hydrogen, gang? And I'm going to read your other comments while you're answering me. Where can I get that hydrogen? Air? No, it's not in the air. Ah, thank you, Chiara, Alessandra, Kai. And it is in the water. Remember water? H2O. There's a lot of H's in there. Do you think some of them have a neutron or two extra? Yup. Ah, so we can get hydrogen from the water. How cool is that? So this is a really big deal, okay? Again, if one of you does this in your lifetime, you're going to be my hero. This is a big deal. If you can get cold fusion, the world's going to love you. Exactly. The surface, 71% of the surface, Ethan's covered with water. Exactly. It's easy to find. Easy to find. Isn't that cool? All we got to do is figure it out. Okay. I know. One of you's got to figure it out. Probably, Okay. I hope that because what's going to happen to the oil industry if we figure this out? What's going to happen to the oil industry if we figure out how to do fusion? What do you think? Think of we get a lot of oil from the Middle East, from Texas, from gas from Russia. What's going to happen to all that if we can use this? Aaron says bye bye. Yeah, you're going to go way down. You're right, Aslan. We're going to have power up the wazoo. We're not going to need as much oil and gas, and that'll change the economy. That would change a lot. But once countries adjust, it's just a really good, clean deal. A very nice, clean deal. Poof, exactly, right? Yeah. No more oil industry, right? And Yeah, you could still use it for plastics, Michael, right? We still could do that with the oil industry, but there'd be less wars, right, to try and get uh, control of countries that have oil. I'll be honest, there have been wars that, even though we don't say it, they probably have to do with getting those oil reserves. Right. Oh, good thoughts, gang. Now, I'm going to leave you for now. We're going to continue with that next week. Um, there is one place where fusion does occur, and we'll see if somebody can guess what that is next week. But for now, I will say have a good weekend. I will try and also send you some assignment to work on next week. Sorry, this week was kind of a mess because I was in school out of the time. Okay, nice. Thanks for the great participation today, gang. Everybody. Bye bye now.